Okay, now we're recording. Let's get, where's, yuck, I just closed PowerPoint. Nope, that's not it. That's it, okay. It must be Tuesday, okay. I'm having 2 Mondays this week. All right, we're back here. Okay, slideshow from current slide. All right, no questions. I don't care for this chapter too much. This is that chapter that always shows up at the beginning of a lot of science books that has sort of a dumb nebulous title like, what is science, okay? But there's a couple of issues that are approached and directed in this chapter that are useful in the rest of the course. So we'll try to get through this as quickly as possible, but without rushing too much, and deal with some of this nebulous stuff. What is science? Well, if you got a text, and most of you don't yet, but a few of you do, the core concept is on page 1 of the text. Now, when you get to the little books, you may have different page numbering than I do. Is that on page 1 of yours? Yeah. Is that page 1 down here? Yeah, page 1. Yeah, it is. So I think most of the numbering will be right until we get to chapter 6, and then they'll be off because we skip chapter 5 in this. We go to chapter 6, and the pages continue. So on page 1, it'll say core concept. Science is a way of thinking about and understanding your environment. Again, a very nebulous, broad, overarching, not very detailed definition. A way of thinking about and understanding your environment. What is science? Here we go again. Some definition people use a search for sense. Yeah, that can be described that way. Finding order out of your surroundings, like you said, understanding your environment, your surroundings. Yeah. And some people think of it as just tools and rules. And in many senses, it kind of is that way, but it really is more than just tools and rules. Now, why they give this picture here, I'm not real sure, except that science is involved all over the place. The construction of buildings, the planting of the sidewalks, okay, the planting of the trees themselves, carrying backpacks, science is involved with that. This guy's having something over one shoulder, this one's strapped across. All these things are dealing with science, okay, without people even thinking about it. Some of these people are probably walking rapidly, some of them may be meandering. That's science. Motion is science. Energy is science. All this is science. So here's the overview of the entire chapter, and then we're going to come back, break it down into smaller issues. So the overview is the first, probably a little more than half of the chapter, probably more like 2/3 or 3/4, is a quantitative description. Quantitative meaning numerical description. The second part is not half, the nature of science. And then we'll talk about some things that you probably talked about in most of the science courses you've ever taken. Okay, maybe a little more depth here. But let's look at the quantitative part. We're going to look at objects and properties. That's the first thing we're going to do. Then we're going to talk about quantifying those properties. That leads then to what measurement systems we use to quantify the properties, and specifically the standard metric units. Okay? Now this book will use both sets of measurements, but probably favoring the metric a little more. That leads then to the metric prefixes, and then, after doing all this about how we measure, what are our understandings that we get from measuring? And this is where kind of the meat of this chapter, the reason we go over it, is in this too. We use all of this throughout the book and what we're going to throughout the course, but this is going to be probably the meat. Then the nature of science, we'll talk about the scientific method, the people behind it, what it means, where it began, how it began, that type of thing. We'll look at descriptions of explanations and investigations, and then leading to laws and principles, models and theories. Again, mostly definition, nomenclature, verbiage, okay? The real quantitative part will come somewhere in here, okay? Which to me is probably the more useful and important part of this. So let's get started with objects and properties. In your text, this is, in Chapter 1, this is section 1.1, objects and properties. What are objects? Things. Things that can be seen, touched, manipulated, moved, whatever. The desk, okay? Pencils, paper, the board, things that you can see, touch, measure, deal with, okay? Those are the objects. The properties, remember objects and properties, properties are the qualities or attributes that are characteristic of the object. So let's take the board here. It's often called a whiteboard. Trouble is, it's not all that white anymore. It's had its years of usage, okay? But it does have a fairly slick surface. You can talk about the properties of this. It does accept ink so you can write on it. It reflects well so you can project on it. Those are properties of this. Whereas the concrete block wall here, you wouldn't want to project on that. You'd have all the seams, the mortar joints there that would be sort of problematic and maybe reading some things. So, yeah, you could talk about anything. For instance, the desk. You could talk about how wide the desk is, how long it is, how tall it is. Those are the properties, the qualities or attributes of the desk. There are also things like the color, the materials. This part is fake wood, okay? This part is some type of metal. This part is some type of plastic, okay? So you could describe the properties, the qualities, the attributes of the characteristics of that object. Now, here is a word I don't think I've ever seen or used outside of this chapter of this book, okay? And that's a reference. Not a reference, but a referent. That's a comparative properties in other more familiar objects. And to me, these are really lame. Sky blue, lemon yellow. It's what are you using as your reference for what blue are you talking about? Sky blue. Well, today sky blue may be really hazy. A few days ago it was a bright cobalt blue almost, okay? So that's sort of imprecise. Lemon yellow, I've seen some yellow lemons that are pretty greenish looking and others that are quite yellow. So again, what are your reference? It's sort of like a reference, but not quite the same. And what I'm talking about here are some of the problems you have with nomenclature. Language can be subjective. What color are your lemons? Okay, are they brighter or darker or richer or darker? Whatever. Okay. Language can be ambiguous. Okay. Sky blue today is not very blue. Okay, it's mostly gray, and sometimes almost circular. Well, it's sort of like this, you're just going in circles there. So language is not always that precise. Okay, when you're describing properties or the reference. You have to be, with science, you have to be a bit more precise, okay? So you'll hear me say several times, in everyday usage, this means this. But in science, we want this. So here are some of your quantifying properties. One thing is measurement, and that's science really deals with measurement. We use quantitative reference, often called units, okay? And the units can be just about anything. Now, most of the time we're going to use standard units, okay? But just pick a unit. Compare the reference unit to the property being described, okay? Now, if I were measuring the desk here, and my reference unit was my chalk holder, okay? Then I might say this chalk holder, this desk is 1 chalk holder, 2 chalk holders, 3 chalk holders, many chalk holders away. This is my reference unit, and then I measure how many of these units are in the width of that desk. Okay? So that's the first step. Compare the reference unit to the property being described. Chalk holder, not too bad for that. If I was talking about the floor width, I would want to use a chalk holder. That's a lot of chalk holders to measure that. So I might want to use something more like yardstick. I don't have a yardstick in here. That would be far better than a chalk holder. Or think of it this way. Now actually what I would do, these are 1 foot squares on here. Yeah, I thought you were looking at them, okay? So count the number of blocks here and you got how many feet they are. Okay? That would be a very reasonable way to talk about the floor. Okay? Pick a reference unit, follow a procedure specifying how the comparison is done. Well, what did I do? I took my chalk holder, that was my reference unit, and put it at the edge of the desk here, as close as I could, put my finger here, and that was 1, 2, remove my finger, 3, and I'm like this, and count the number. That was my procedure specifying how the comparison was done. Not very precise, but at least gave me a general idea. And then count how many of those standard units describe the property under consideration. Identify your procedure and then count how you're going to do that. Okay? Now, chalk holders are not the best thing. Okay? Tiles are not bad because they're 1 foot tiles until you get to places where you've got portions of them and then you estimate. But let's think about on a bigger scale. What do we usually use to measure as our reference units? Think of name something. Say for distance or length. Say again? Mile, that would be a good one. Now if I was measuring the length of the desk, would I want to use miles as my unit? No, that's going to be way too big a unit. The number would be incredibly tiny. Okay? But if I was going from here to Tuscaloosa, yeah, miles would be a great unit to use for that. Okay? But if I'm measuring the length of the desk, what would be a standard unit for it that you use here? Inches would be good. Okay? Or if you're metric, you might say meters or centimeters or something like that. Or possibly feet if you wanted to use feet. But inches are pretty good. But if I was going to here to Tuscaloosa, would I want to measure that in inches? No, I sure don't want to do that. You see, compare the reference unit to the property being described. If it's a desktop, inches are great. If it's a long trip, inches are not so good. Miles would be far better. Okay, so you get the general idea of what they're talking about here. Now, it's essential that if you have a number, like maybe 8.5 chalk holders, I just made up a number, I need to say chalk holders. If I say 8.5, why is this desk? Well, it's 8.5. Does that make any sense? No. Now, when you're answering a problem, sometimes you're just going to give me a number. I bet you will. Some people always do, with no units attached. With no units, the number makes no sense. If I say, how far is there from Tuscaloosa? 312. 312 what? Okay? I can't even imagine what that could be. So that doesn't make any sense unless you put a unit with it. Now I'll give you an example. It's not precise by any means, but it did happen. This is a real life problem that did occur. Y'all probably are way too young to remember. After World War II, I wasn't around in World War II, by the way, just to put that straight. But after World War II, we had fought against Germany and also Japan. But the Germans, they were pretty brilliant people. And they had developed rocketry we hadn't developed. Okay? We were very fortunate that we had several Germans left Germany and came to the U.S. and helped us to develop the atomic weapon before they did. Okay? Otherwise, it would have been a pretty miserable sit-up. Okay? So, after World War II, our allies had been Europe, America, in Russia. Okay? But as soon as the war was over, Russia, and I think they were still called Russia, they're not Soviet Union, and the West, they almost immediately became enemies. So they all went racing to get as many of those great German scientists as they could under each count. And we got as many as we could, and the British and the French got what they could. The Russians got as many as they could. And that began the space race, because the Germans had used rockets to go over the English Channel and bomb Britain very effectively, too, very destructively, too. So it was a whole new ballgame. So the space race began. And guess who started off winning it? The Russians. They got the first spaceship into outer space, the first living thing into outer space. I think it was a monkey or something. They got the first man into outer space. They made the first orbit of the Earth. They were beating their socks off, okay? It looked like for a while, okay? And somewhere along there, President Kennedy then put out the challenge. He wanted to make it to the moon within a decade. And in order to do that, we had a space organization, I think it was called NACA, I don't remember what that stood for, but then it was changed, at some point changed to NASA, NASA, National Aeronautics and Space Administration. And they, in order to meet that goal, had almost unlimited funding. They poured the money into it wherever they needed it. So NASA gathered lots of great scientists. They worked out their own problems. They built their own rockets. They did their own propulsion studies. They did everything pretty much in-house. But it was a pretty expensive process. Well, we made it to the moon. We got there first, way first. We got there fairly safely. Had a few problems. But overall, things went pretty well for us. But after a while, we were beating the Russians, almost the Soviet Union by this time. And after a while, it was pretty clear we were way ahead. And Congress or somebody got to worrying about, hey, we can't just be giving NASA these blank checks anymore. We've got to put some sort of controls over it. So what they said was, NASA, we have all these universities with great minds. We have all these national laboratories with great people. Start farming out some of your things. You don't have to do it all yourself. You're too expensive. So it was a Mariner project. That was a project to go to Mars. I think we had already had a couple, but this was one, and they said, nope, you can't have a blank check. You need to farm it out to some of these other people, let them absorb some of the costs. So they broke the project down into pieces. They let out bids on the first is to do the launch and to start the orbiting around the Earth. Another group was responsible for leaving orbit of the Earth and going to Mars. And then another one was to reach Mars and then start orbiting Mars. And then another was to do the scientific investigations while we were there. Okay? Something like that. Okay? And the groups were to communicate with each other. Of course, they needed to, because the group got us in the orbit here and how to leave orbit there. They had to be communicating. So they did. And everything seemed to be going well. They came in with a lower bid. Wow, we're going to do this project for probably only $6 billion. Wow, a new indoor record of low bid, So everything else had been way expensive before then. So things were doing pretty well. Launch, perfect. Orbit around the Earth, perfect. Transition to leave to go to Mars, perfect. Got to Mars, went to turn to go into orbit around Mars. The spacecraft turned and crashed right into Mars. What went wrong? Okay? They started studying back. Someone had forgotten to put what units they were using. Everybody assumed they were either metric or English, I don't know which, but they hadn't been. They were the other unit. So the next team assumed this was what their measure was, And they did theirs based on the other because someone forgot to put the unit down. And that's for a $6 billion mistake for one unit. Okay? Hopefully, sometime during your lifetime, you'll be in a position that you can make a $6 billion error. But I hope you don't make one, especially for something that trivial. Okay? But it did happen. It did happen. The only data they got was from what they collected there, and as the spacecraft was rushing toward crashing into the planet. Maybe 15, 20 minutes of data. That's all we got for those $6 billion. Okay. Units are important. Units are your friends. Keep up with them. They will keep you from making some really dumb errors. We'll talk about more of that later. So that gets to measurement systems. Okay? Now, this book calls it, as I've mentioned, the English system. Guess what? The English don't use the system anymore. Officially, anyway. Most English people still use miles and inches and things like this. But England, Great Britain is officially a metric, SI subscriber. Everything official does that. Okay? The only people that still use the English system is us. And a few of our trading partners who do most of the trade with us, so they use it. But most of the rest of the world, all the other industrial countries use SI. Okay. So the English system, many of the units were based on parts of the human body. A yard was the distance from your nose to your fingertip of an outstretched arm. Okay? That was how it was defined. Okay? Originally. A foot, just about a man's foot. See when I did that? That just about covers on like mine's a little bit longer than a foot. Okay? That's where the foot came from. Inches was about your joint on your thumb. The first joint on your thumb. Okay? Now, of course, Shaquille O'Neal, if he did this, that's a long yard. Okay? His arms are way. Y'all don't even know who Shaquille O'Neal is. He's the Papa John's guy now. Yeah, he's the basketball player. Yeah. But pick whoever the longest. Yao Ming, he's already retired. Any of those. Their feet. They would be much longer feet too. Okay. So, many based on body parts. Another, one king said, an inch would be 3 barley corns lying end to end to end. And guess what? On a real good year, they may be big old barley corns. On a bad year, that could have been not the best way to measure units. Okay? Now, how many inches in a foot? How many feet in a yard? How many yards in a mile? 760. What nice uniform numbers these are. Okay, how many ounces in a pound? 16. How many pounds in a ton? 2,000. Finally got something that's a reasonable number, okay? How many ounces in a ton? 8. How many tons in a pint? 2. How many pints in a quart? 2. How many quarts in a gallon? 4. That's where the quarts come in. Hey, where's the uniformity here? Where is the systematic way of doing it? That's not really good science. But they're based on all sorts of things, not reasonable things, okay? Body parts, for instance. Anyone know what a cubit is? Well, most scholars should know this. It's about 18 inches, foot and a half. It's about the length from your elbow to your fingertip, about 18 inches. So, for a long time, you can go into all sorts of things. The metric, now there's actually 2 systems here. The metric system was what they first came up with. Later they named it SI. That stands for System International, which means International System. You see, the French came up with this. And if you have studied much history, you know that for much of Europe's history, the French and the English have been at odds with each other. Only World War I and World War II were about the only time they were on the same team. Okay, most of the time they were fighting each other. Well, the English had their system, and theirs was fairly uniform. But the France was a much bigger country, much broader, and they had these little Alsace-Lorraine and Brittany and Normandy and Paris, all these different pieces of France, and they always tried to cheat each other. And they could get away with it sometimes. So their system was not very uniform. So they came up with this system, which was supposed to be very uniform, and is. Now, it was established in 1791. Does anyone remember what was happening around 1791? The French Revolution, you're absolutely right. So this was done about the same time. Everything else was going to pot in France, so why not let's change the whole system and get something much more uniform? They were trying to get rid of the monarchy and set up a more reasonable civilian government. They didn't do a very good job of that, but they did do a great job with this. So that's why it's System International, or SI system. Now, here's the reason we call it SI rather than metric now. 7 basic units. Length was in the meter. Okay? And how they defined the meter was they took the distance from the North Pole to the equator, and the most direct way they could measure it, probably through Paris, France, I'm guessing, and they came up with the best estimate there, and they took 1/10,000,000th of that and said, that's going to be our meter, okay? Now, the meter happened to turn out being just a little bit more than a yard. If a yard is from your nose to your fingertip, the meter is about from the opposite ear, a little bit longer, 3 and a few fraction of an inches longer than a yard. But they're basically the same. So, 100-yard football field, 100-meter soccer field, it's just a little bit different. Yeah, a little bit different, but fairly close. Okay? Now, in the metric system, not SI, the unit for mass was gram. But it just turned out a gram was so incredibly tiny. They said we need something bigger than a gram. So what does the kilo stand for? 1,000. So that means 1,000 grams. So SI, the standard unit, is kilogram. Metric would be gram, but SI would be kilogram. That's the only one of these measurements that they use the prefix for. Now, what do we use for time in the English system? Second. What do we use metric or SI? Second also. That's just so uniform, they didn't want to mess with that. So that's the same. Now, ampere. What does that measure? Current. Electrical current. What do we use in the English system? Ampere. Why? Because this came out after 1791. Okay? And so after that, when something new came up, we tended to go with this. Okay? Temperature, officially SI is Kelvin, not Celsius, certainly not Fahrenheit. The most other countries use Celsius temperature scales. We use Fahrenheit scale, but the official SI is Kelvin. We'll talk about that in chapter 4. Okay? In chemistry, and we won't actually get far enough along to do this, but the unit of material in a chemical sense is a mole. Okay? Why they leave off the E wrong, they just write off mole, but yeah, the abbreviation is that. And for light intensity is candela. Okay, CD. Now, I see that most of these, meters, kilograms, seconds, moles, candela, are lowercase, but here, ampere and Kelvin are uppercase. Why is that? Named after somebody. An ampere named after Louis Ampere, a French physicist who did a lot of the early work with current. And Kelvin is actually not named after somebody, but it was the title of somebody. He did much of the early work in thermodynamics, so they named that scale after him. Fahrenheit was named after German scientist Fahrenheit, so that's capitalized. Celsius named after Anders Celsius, that's capitalized. Earlier, Celsius was called the centigrade scale, centi meaning 100 measured between, and that was lowercase c, but they moved it to capital C after Anders Celsius, who actually developed that scale. Okay, so these are the 7 basic units. All other units are derived from these. So voltages are derived from amperes, believe it or not. Coulombs, charge is derived from that. Everything else, all your different temperatures from this one. All your time, minutes and hours and years and whatever, comes from seconds. Then things that are mixed things like area would be square meters, volume would be cubic meters, and then capacity would be measured in terms of those. Mass is kilogram. Force is kilogram meter per second squared. So you can have all these different combinations of things, but these are the basic 7 units. We're not going to use all 7. We're going to use meters all the time, kilograms lots, seconds lots, amperes only in chapter 6, Kelvin mostly in chapter 4. We're not going to even get the mole and candela at all. Okay, so those are the basic units we're going to use: length, mass, time, current, and temperature. Okay. Now, over here in the English system, they don't list them here, but the basic unit for length there is foot, not yard, but foot. Yard is closer to a meter, but we use feet as a basic. We don't use anything for mass. There is a unit for it, but I bet you've never in your life used it for mass in the English system. The slug. Have you ever used it? One time. Was that in a science course? Yeah, it was in a class. In real life, have you ever gone into the grocery store? I'd like 3 slugs of potatoes, please. They were good. Out of here. Okay. We don't want you here. Okay. What are you talking about? No one uses that except in a science book. It doesn't even have an abbreviation. If you use it, you have to spell out slug, S-L-U-G. Okay. It doesn't even have its own abbreviation. Okay. Seconds we use the same. Ampere we use the same because it came out after they did the split. We usually use Fahrenheit, degrees Fahrenheit. They use Kelvin. SI is Kelvin. Mole is used in both because that came out after this was developed. And then we still use candela, but we very seldom talk about light intensity, unless you're studying light intensity. So that's the English system. So, what are these standard metric units, or SI units, for the 4 fundamental properties: length, mass, time, and charge? Okay? Not getting into temperature yet. Okay? Well, it seems like they could have come up with something better than this. But we say a meter, which was 1/10 millionth of the distance between the North Pole. That's really hard to measure. This is any easier? The distance that light travels in 299,792,458 of a second. Yo, yeah, right. That's really easy to measure. But that is officially what 1 meter is. Mass is reference to a standard metal cylinder that's kept inside a hermetically sealed vault inside a thing in Paris somewhere. I think it's Louis Pasteur Institute or somewhere like that. They have that, and no one ever opens it and touches it because they don't want it to ever change. They just copy it, and everybody uses that. Okay, that's mass. 1 kilogram. Time. Yeah, right. Refer to the oscillation of the cesium atom. Yeah, okay. I can do that. No, rather bizarre, but that is something that very, very precise. And then charge. We'll have to wait till chapter 6 before we do that. All the other properties, volume, force, energy, all these things are derived from these. Okay? They left off temperature here, but we'll use that in chapter 4. Okay. So here are your SI, System International, base units. The base unit for a link is, of course, the meter. We already said that. Its symbol is little m. Okay. In French, meter means to measure. So this is one measure. Okay. Mass, in the original metric unit, it would have been gram, but they decided to go with the 1,000 grams, which is kilogram, kg. Time, second, standard across the board. Electrical current, ampere, across the board. Capital A because it's named after somebody. Okay. Temperature, Kelvin. We've got it back in here now, and that's capital K because it's his title, Lord Kelvin. Amount of a substance, in a chemical sense, is mole. That's different from mass, but that's the mole. How much of a substance it is there. How many molecules, you might say, is MOL. Okay? And luminous intensity is candela. We're not going to use that one at all. We won't use moles either. We'll come close to talking about it. All right. Now, let's talk about the metric prefixes. This is what makes the metric system so uniform. Unlike all the different conversion factors you have to keep up in the English system, the metric system, it's pretty standard. Everything's based on powers of 10. Now, anywhere close to your basic unit, like meter, gram, those, you use 1 power of 10. For instance, 1 meter would be 10 decimeters. Okay? Big decimal point, that's 1/10. So this is 1/10 of a meter. If you take 1 decimeter, now this is not a meter in length, so this is not a decimeter in length, but if you represent that and expand that and make this a decimeter, that's getting probably closer to what a decimeter is. 1/10 of that is a centimeter, or 100th of a meter. Okay? Should be easy to remember centi being 100. Oh, what's that? 1 cent. And how many of these make $1? 100. 100 centi. This is a centi dollar. 100th of a dollar. Okay? So a centimeter would be 100th of a meter, 1/10 of a decimeter. But then we take that centimeter, and by the way, this isn't what it was based on, but this is just a general thing. The width of your little fingernail is approximately a centimeter. The length of your thumb is approximately an inch. So it takes 1, 2, and about 2.4 centimeters to make 1 inch. That is an exact conversion, by the way. Okay, so this is closer to an inch. That's close to a yard. This is close to an inch. Decimeter isn't really close to anything. Okay, so 1/10 of a centimeter would then be a millimeter. What's a millimeter? I don't have a dime on me, but that penny will work. That's approximately a millimeter. A dime would be closer to a millimeter. Okay, so the thickness there. Okay, so that's pretty small. So this is bigger than a real millimeter. It's just a standard. Okay. But everything's based on powers of 10. Now, when you go larger than a meter, 10 meters is called a decameter. D-E-K-A, D-E-C-A, D-E-C-K-A, I think it is. What are 10 meters called? Decade, same thing, decameter, a hard C, or K. 10 decameters would then be a hectometer. Hecto, 100. Okay? That's sort of easy to remember. The only place I've ever heard of anyone using a hectometer is in measuring land. What do we use in the U.S. customary or English system to measure land area? Acre, exactly. So when they got to measuring land in the SI unit, the standard would be a square kilometer. Square kilometer was way bigger than an acre. Way, way bigger. Okay. So they did the same, but it's closer to what an acre is. And by the way, I should have said this a couple slides ago. If you're doing anything scientific, always use SI. Even in hospitals. Does anyone know anyone who works in a hospital? Okay. Who, nurse or doctor?
She's a nurse.
Nurse. Okay. What hospital? UAB. Is she anything to do with newborns? No. But if you were, certainly what they tell the parents is how many pounds and ounces and how long in inches. But what they report on the charts is how many kilograms and how many probably centimeters. Okay. Everything is done scientifically in that. Even GM car. Back when I was a boy child, everything was in 3/4, 5/8, 7/8. What is it now? All many. Why? We live in a global world. Where the GM is going to compete globally, they have to make all their parts SI. And they do. Okay? If you have an old wrench set that's 4s and 3, you have to have something that's only made in the U.S., but it won't work in your car very well. And that's what everybody used to have. Okay. So anyway.
Hey, it's 5:50.
Oh, okay. Good time to call roll again. Okay, thank you. I'm also learning names and faces. Logan, okay. Jay, got it. Ethan, I know. Amanda, I know. Jonah, I know. Patrick, I know. Thomas, I know. Latricia didn't make it in today. Frank, okay. Jose didn't make it in today. Is he also a GM guy? Jose Mendez, okay. He's the only one I didn't know that's not here. Mark. Was that Mark that was sitting back there? I think it was, wasn't it? I believe that's right. Diamond is here, and Ryan is here. So we only lost one, and that was Mark. Okay. Now, here's the other thing, folks. Remember when I was asking inches in a foot and feet in a yard? Those were length measures. Then when I went to capacity, how many ounces in a cup, and that was capacity, or volume, you might say. And then when I talked about weight, ounces in a pound, all those conversions were different, right? But in the SI units, when you're talking about a decimeter, you could talk about a deciliter. You could talk about a decigram. You could talk about a anything. That symbol means the same thing. 1/10 of the major unit. Okay? And I got to hecto, but I didn't get to the next one. 10 hectometers would be 1, we've already said it, kilometer. Okay. So, when you're talking about SI, all of the prefixes are used for every measure. So you don't have all these different conversion factors. They're all the same. All the same. All powers of 10. Now, what if we get far away? For those closest to the basic unit, like meter, you do 1 and 1 and 1 power of 10. 1 and 1 and 1 power of 10. Once you get outside that, past millimeter and past kilometer, we don't go by single powers of 10, we go by 3 powers of 10. Thousands. Okay? So you jump from a kilometer to a megameter. That's a million. This is 1,000 meters, that's a million meters. Then you go to, and think of this for you computer people and also frequency people, things like this. Think in terms of that. If you have kilobytes, which is very small, 1,000 bytes, then you have megabytes, gigabytes, terabytes, okay? Or frequency, you could be talking about kilohertz, megahertz, gigahertz, terahertz, or nuclear weapons. No, I mean, you could see kilotons of dynamite, megatons, or electrical power generation. Kilowatts, megawatts, gigawatts. Okay. Everything goes up by powers of 3 past 10 to the third and 10 to the minus third. 10 to the minus third. You always do. Oh, let's go to the smaller ones. After millimeter, which is 1,000th of a meter, you go to micrometer, which is 1,000,000th of a meter. Okay? You take each of these and split it into 1,000 pieces. Okay? Okay. Ooh, that's pretty small. Okay? And that's micrometer. Well, there, we'll get to this later. We've already used little m here, and you went to megameter here, you have to use a capital M because you already used little m. Well, all the bigger ones, then you all capitalize them. Not because they're named after someone, but because they're talking about such big units. Okay? But micrometer, you use a Greek little m, which is that. It looks sort of like a U with a long tail on the front end. That's micrometer. And then they get smaller from there. We'll see that table a little bit later. Okay. But everything's a power of 10, or 3 powers of 10. So, what do we understand from these measurements we're making? Well, what we gather is our data. Now, notice I almost said is data. It's not is. Are. Data is a plural word. If you just had one piece of information, that would be called a datum. Multiple is data. That's the plural of data. Okay, once you have data, then you can look at ways to compare data. One way is ratios. Okay? Do we ever use ratios? In automotive, do you ever use ratios? What? Name the ratio. Exactly. And you have gear ratios, number of teeth on the gear, even driving your car, miles per hour ratio, how many miles you go per hour, how much time, or efficiency, miles per gallon. You're always looking at ratios. You get your data, and then you compare them in different ways, ratios and generalizations. One ratio we'll look at is the density ratio. Density is mass per unit body. Density, mass per unit body. There are others that you use. Think of your tire pressure. The old way we measured that was pounds per square inch, force per unit area. Okay? Now we use kPa. You know what that stands for? Kilopascal. And what's a pascal? A Newton per square meter. Newton is the SI unit for force, just like pound is the SI is the U.S. customer or British unit for force, and square meter is the standard unit for area. Meter is the standard length for a square inch. Way smaller. That basically is a square inch. A square meter is below the doorknob to the floor of that door. A lot of square inches in 1 square meter, so yeah, very different. That's why you have to use kilopascals, because per square meter is very small. Okay. Symbols and equations. I just gave you the one for density. Density is mass per unit volume. That's an equation. Okay? Symbols would be, we'll talk about those later. And then problem solving made easy. Isn't that nice? We'll talk about, I don't count it, it does make it easier anyway, but makes it reasonable of how you go about solving problems. So let's first look at data. Now we're going to look at each of these things separately. Data. That's the measurement information used to describe your objects we were talking about, conditions, like maybe weather conditions, stuff like that, events, how many people were there, how many cars were there. We happened to be driving home from Georgia Sunday evening, not good, because we were hoping to get through before the race was over, but guess what? Rain canceled the race. So events, how many cars were there, how many people were there, how many hamburgers were there. We won't get into beer cans, but whatever. Okay. Changes of things. Okay. We talked about the temperature change from last week to this week. Huge. Okay. You use data to measure that. Here is one way to look at data. The dimensions of a cube. Okay? If we're talking about a cube, what makes a cube a cube? Second? What's that?
3 dimensional.
It's 3 dimensions for sure. And what's special about those 3 dimensions? They're all the same measure. Okay? So if this has a length of S units, then its height is going to be S units, and its width is going to be S units. Now that doesn't look like it is, but because you're trying to draw a 3-dimensional object on a 2-dimensional board, it's hard to do. But that means, so let's look at some of the things. The cube here, each edge is S units. Every edge there is S units. That's what makes a cube a cube. Now the other thing that makes a cube a cube is all the angles are the same, 90 degrees. We're not getting into angles right now, so we'll just leave it like this. But that's the other thing that makes it. If they weren't the same, that would be a rhombus or a rhombohedron or something like that. But if they're all 90 degrees, then that's true. The area of one face of this cube, if its length is S and its width is S or height is S, then the area of that would be S times S, which is S squared. What would be the area of the entire cube? Well, here's a face, there's a face, back there's a face, over here's a face, there's a face, and there's a face. 6 of them. So that would give you 6 times the area of one face, that would be 6S squared, would be the total area of that whole cube. The volume of a cube, on the other hand, would be S times S times S. So that would be S cubed. Okay? Notice we treat the symbol here just like it was a number. And if you were actually using a length measurement, like feet, you would do this area in square feet, or square inches, or square meters. And this would be 6 square inches, or square feet, or square meters. This would be cubic feet, or cubic inches, or cubic meters, cubic meters. You would use your unit and use the same superscript to represent. You use that unit 3 times. Okay, so that's data that we could collect. Collect the length, calculate the area, calculate the total area, calculate the volume. Okay? Now, ratios and generalizations. Taking the same cube we just had, now we're going to say those units that we had were in inches. S was in inches. Okay? What we're going to do, the ratio helps you analyze through a quotient 2 different measures. So what we're going to do is take a 1-inch cube. That's 1 inch by 1 inch by 1 inch. Okay, just 1 inch cube, inch by inch by inch. Okay, pretty small cube. They call it little sugar cube. It won't sweeten anything. Okay, that's what we're talking about here. Okay, one side is going to be 1 inch. One face would be 1 square inch. But how many faces you got on that cube? 6. So 6 square inches would be your area, total area. What would be the volume of that cube? 1 inch by 1 inch by 1 inch. 1 cubic inch. So what's the ratio of the area to the volume? 6 to 1. Now, I don't like this example for one reason. They leave off units here. This should be what we call a per inch, because you have square inches on top, cubic inches on the bottom, so you have a per inch is your unit. That's a rather strange unit, so they leave it off. Actually, better would say 6 square inches per cubic inch. That would be the most precise way of saying it. So they're leaving off the units for now. Shame on that. Okay, if you had a 2-inch cube, what's the area of one face if you had 2 inches? 2 by 2 is 4, and you have 6 faces, so that would be 24, right? 6 times 4 is 24 square inches. But what would be your volume? 2 by 2 by 2 What's your ratio now? Area to volume. 24 divided by 8 is 3. Hey, wait a minute. As your area and your volume got bigger, the ratio got smaller. Okay? Interesting. Well, what if you had a 3-inch on each side? What would be the area of one side? 3 inch by 3 inch. 9 square inches. How many sides you got? 6. 6 times 9 is 54. 54 square inches on that cube. That's the surface area of the cube. What's the volume of that cube? 3 by 3, 27. What's the ratio of that? 2. You got bigger here, bigger there, but your ratio got smaller. Now, what's the ramification of this? Okay? Believe it or not, crushed ice melts faster. What? Okay? Because if you take a block of ice, a big block of ice, okay? Let's determine how much. Say 1 kilogram, 1 pound, whatever you want to say. That block of ice is going to weigh whatever you want it to weigh, right? Now it has and if it's a cube, then it has a length, a width, and a height. So you could get the area and you could get the volume, just like we did here, whatever it was. Now let's take that and cut one slice, cut one dimension in two. You have the same amount of ice, right? You haven't lost any ice. But now you cut it in two. Two of those faces that weren't faces before, now you've exposed 2 more faces. So you've increased the surface area without changing the volume of the mass or anything else. Cut it again, you've increased the surface area without changing the volume at all. The total volume is still the same. Cut it again and again, so you keep increasing the surface area, and not changing the volume. Because that's still block of ice. You put it all back together, it'll still be the same volume. Okay? So, by the time you crush the ice, you now have way more surface area, so your area to volume ratio is going up. As you get smaller and smaller pieces of ice, your area to volume ratio keeps getting larger and larger, meaning you got more area per unit volume, more exposed, so it's going to melt faster. So that's why the crushed ice, the icy that you get at the store, drink that too fast, you're going to get a headache. If it's got big cubes in it, it's going to take a while in stirring to get it to cool your hot tea, you know. Crushed ice will cool it much faster. Okay? On the other hand, I was in the Navy, and we didn't have this so much, but in the Army they had what they call KP. Anyone ever heard of that?
Kitchen patrol.
Kitchen patrol. And what was the most famous thing they were doing on kitchen patrol? Peeling potatoes. Okay? Well, they ate a lot of potatoes. Now, would you rather peel a 5-pound bag of large potatoes or a 5-pound bag of small potatoes? Why? Because your surface area to volume ratio is so much less with a bigger potato. So you got a lot less peeling to do. Okay. Absolutely. You peel some potatoes before I done. Yes, I can tell. All right. Large potatoes. They're not easier to peel, but it's easier to peel a pound of them than it is a pound of small potatoes. That's what they mean. So your area to volume ratio can give you lots of good information that you probably never thought of. Now here they showed it in a graph. Okay, here is your 1 inch. Let me get this right. Yeah. 1 inch. This, okay. Here's your area. Here's your volume. And here's your area to volume ratio. So this is the one. Oh yeah, there it is. The light blue is the 1 inch. The area, the volume, area is 6, volume is 1, and the area to volume ratio is 6 again. So that's the same. Then you go to 2 inches, the area is 24, the volume is 8, but the ratio is down to 3. It's decreasing. And with the large then 3 inches on the side cube. That would be 54 square inches, 27 cubic inches. The ratio would be down to 1. 2. And that would be 2 square inches per cubic inch. I like to use the units. So your table shows what you see. This is the table, that's the graph, and it illustrates that in a different way. All right. Let's look at a specific ratio now. And this is the density ratio. We've already talked about it, and I've already told you what it is. It's the ratio of the mass of an object to the volume of an object. Now, what makes that so special? Anything particular? This was a story about Archimedes. I don't know if any of you remember Archimedes. Famous for anything? Flotation. Okay. Buoyancy. He came up with that whole concept. He did this hundreds of years before Christ. I mean, way BC. Okay. He was a pretty sharp dude. Way before much of the rest of us had any idea of anything. Okay. Now, he worked under this king. And this king was a pretty powerful king, mostly because he had Archimedes working under it. People sort of respected him. One of his rivals sent him this elaborate, beautiful, fancy crown. And it looked like it was pure gold. But he didn't trust this guy at all. And he said, I think he's cheating me. I think he's trying to give me something making it look fancy, but it really is cheap. Archimedes, figure it out. Is this pure gold or not? He said, sure. He pulled out the pocket. He said, no. Is this pure gold? I don't want it damaged, so you can't harm it. You need to tell me if it's pure gold or not, but you can't scratch it. Archimedes said, whoa. Okay, let me think on this. Okay. And supposedly, back then, you probably heard of this in Roman times, but this was back in Greek times too. They had public baths. Okay, so they didn't have running water in everybody's home, so they had public baths. And he had gone to take a bath, and he noticed, of course, when he got down into the tub, the water went up. And he said, Eureka, which means I think in Greek, I got it. What he had was this principle of buoyancy. Because you see, pure gold, that crown is going to displace its volume of water, just like he did when he sat down there. So that's going to be fixed. He could measure the weight of that crown, or the mass of it, and find out its mass. Actually, that probably weight. And then look at the ratio of the mass to the volume. Because you can tell exactly how much by displacing the water, catching the water as it spilled out, measuring how much water it got. So now he had a ratio of mass to volume. He could do that to a gold block, and it was going to have the same density. See, density is an intrinsic property independent of how much you've got. So a block of gold, if it's a pure block of pure gold, is going to have a certain mass, and you can measure its volume or dunk that in the water too, okay, and get its density, compare it to the density there. Now, supposedly, I don't know if this is true or not, but supposedly he was so excited about discovering this that he got up yelling, Eureka, I've got it, running through the streets to go tell his king. But like good scientists, he was sort of absent-minded, forgot to get his close. So anyway, that was the story. Whether it actually happened that way or not, I don't know. But that's exactly how he solved this problem. Okay, whether he had clothes on or not. Okay. Now, it's a characteristic of a given material. All gold, a little bit of gold, a lot of gold, is going to have the same density. Same thing with copper, aluminum. Whatever you've got, if it's a pure material, whatever it is, it's going to have the same density whether you've got a little bit of it or a lot of it. Now, I mentioned that he may not have measured his gold in mass, he may have used weight, how many ounces of gold or pounds of gold or whatever, then that's weight per unit volume. It's a different number, but it's equivalent to measuring the same thing. And there's a reason for that. We'll get into this a little bit later. But weight and mass are completely different measures, but they differ only by a constant. And the constant is the acceleration due to gravity. And since everything we do is pretty much on the surface of the Earth, that's the same acceleration due to gravity everywhere. So we can measure pounds of potatoes or slugs of potatoes. We go with pounds. Okay. Here is the formula, remember, back here, a couple slides ago, right here. Whoops, not there. Here, symbols and equations. Here's the equation that we just used. Now, for some reason, density uses the Greek letter rho. That's the Greek letter rho. Looks like a P, but it's equivalent to our R, but that's the rho in the Greek alphabet. So density of rho is equal to mass per unit volume. Now you might notice mass is a small m, which is fine, but volume is a capital M, a capital V. Why would that be? We'll realize this a little bit later. When in physics, remember you have to be fairly precise. A little v almost always represents velocity. Capital V represents volume. So that's why it's a capital V here. We're not talking about velocity. That wouldn't make any sense here. We're talking about volume. So this is rho, or density, is equal to mass per unit volume. Now what units would we use? What's our SI unit for mass? Kilogram. Okay? SI unit for volume? Length times width times height. What's the SI for length? Means to measure. Meter. Meter times meter by meter, cubic meter. Kilogram per cubic meter. Now that's not a very handy unit. I would much rather do gram per cubic centimeter. It's a much more usable number, but the standard is kilograms per cubic meter. And that's what you would measure your mass density in. Okay. Here are some examples of these intrinsic properties, characteristics of the material. If you had a block of gold that's 1 centimeter, 1 centimeter, 1 centimeter. Now we're not using SI, we're using the old metric. This would be 19.3 grams per cubic centimeter. If you had this, run to the bank, okay, because this is really valuable, okay? Put it in safety deposit bonds. That's a lot of money right there. If you had that same 1 cubic centimeter of iron, it's only going to be a mass of 7.9 grams because the density of iron is less than half the density of gold. Gold is really dense, okay? Water, now you might say, isn't that unusual for that to come out exactly 1? Not really, because when the French were doing their distance from the North Pole to the equator through Paris, said 1 10 millionth of that is a meter. They also had to come up with other things. So they said, what are we going to do? Well, that meter is pretty long, okay? So let's use 100th of a meter or centimeter. And then let's have a cubic centimeter. That would be about one little finger here, one little finger there, one little fingernail there. Okay, that's a really small cube of sugar. It's not going to sweeten anything. Okay, that would have, they'll say, let's get the mass of water in that little cube to be 1 gram. That's how we're going to define our mass unit. 1 gram was 1 cubic centimeter of water. So that's why it's an exact measure. 1.0000 grams per cubic centimeter. Okay? Now if you have that same cubic centimeter of air, that's going to be 0.0013 grams. Believe it or not, air still has weight, right? But it's not very much. Now, goes back to your tire pressure. When you're measuring that, that's called gauge pressure, right? Because does anyone know what, I mean, PSI, what atmospheric pressure is? Atmospheric pressure in PSI. 14.7 PSI. What's giving you 14.7 pounds? Okay, now a square inch is about that. And think of how many square inches you have in your body. It's a lot of square inches. 14.7 times that. Just think 15 times that. That's a lot of weight on your body. What's providing that weight? The air, the atmosphere. That's why we call it 1 atmosphere of pressure. That's why the gauge pressure subtracts off that 14.7, because everything's going to be 14.7. So your gauge is measuring how much it is above that. Okay? So even though this is a very small density, you have a lot of air above us, okay? Enough to be. Well, why does that not crush us? If you were to multiply the number of square inches in your body, if you could calculate that, multiply it by 15, that's a lot of pounds. A whole lot of pounds. Why aren't we crushed by that? Because we're pushing back with more than that. We have pressure in our body. If you ever were to prick your skin, the blood comes out. It doesn't suck air in, right? That means the pressure inside you is more than the pressure outside. Which leads to another sort of gruesome thought. One of the most dangerous jobs, I think, that has ever been performed during my lifetime. I didn't do it, of course, but I heard about it being done. Remember the space race we were talking about? The Russians got up, I think they got up the first space station. It was called Soyuz, something like that. We got up some after that, and since then we have the International Space Station. Soyuz is nothing compared to that. But Soyuz, they had to replenish and everything for the cosmonauts who were on Soyuz. They had to get more food and water and other things like this. So they would send up these cargo ships, but they weren't manned, and they were all controlled by computer or something. And some of the controls weren't the best, or either the drivers inside the capsule weren't too good. I don't know who it was, but one of those cargo ships crashed into Soyuz and burst the seals that kept the atmosphere inside there, and the cosmonauts had to rush to a secure, very small space on the inside, which had been built for that very purpose if that ever happened. So they were stuck inside, and we had to send up our space shuttle to repair it for them, because they didn't have that capability. With our space shuttle, we could move people around and stuff, get it back easily, fairly easily. So we sent up astronauts to help. We cooperated pretty well. And we sent up astronauts to repair that jagged metal, broken stuff on the space. Just call it Soyuz space station, whatever you call it. And that had to have been one of the most dangerous jobs ever. Because you see, there they were in these big, bulky pressure suits. Why pressure suits? Because outer space doesn't have any atmospheric pressure. Zero. So the space suits that the astronauts were wearing had to be pressurized, about 14.7 or something close to that, just so they would be okay. If when working on that jagged, broken metal, they would have ripped their spacesuit, there goes the atmosphere, there goes the blood, gases, everything out into space. They would have been gone like that. It would have been radiation, that would have gotten them to the top. No, the pressure, everything, their eyeballs, everything would have been shooting out all the fluids and gases in their bodies. Pretty gross. jobs ever, most dangerous jobs. But anyway, that goes to pressure, not ratio, not density. Okay. Now, symbols and equation, we just saw some. Right back there, there's in symbols, rho being the symbol for density, little m being the symbol for mass, capital V the symbol for volume. The equation, rho is equal to m times v, the m divided by v. Which leads me to something else. Anytime you have a ratio like this, you can immediately come up with two other equations. Does anyone know how to do that? Okay, first you could say multiply both sides of this by v, couldn't you? And that's going to wipe out the v here, and that gives you mass is equal to rho times volume, right? Or, I think what you were suggesting, divide this by rho, and now the rho's go away, and you have volume is equal to mass per unit mass density. Here you have three equations. Let me go back and erase this one. There's your first equation. Oops. Let me keep that. Here's your... get out of there. Okay. Here's your second equation, and there's the third equation. Three different equations, all telling the same story, but from different perspectives. Now, have any of you used triangles or circles to help with these kinds of relationships? You know what I'm talking about? Okay. I was in the Navy, like I said. In Navy schools, they love these things. I always did it just based on the units. It was easy to keep up with. They use this. Either a triangle, and they have a dividing line and then a vertical dividing line. That's the multiplication line. Or you could use a circle, either one, same thing, dividing line, and then another one. And put the one that stands by itself, either on top, like mass, or by itself, put that here, and then put the other two down here, rho and v. Or you could do it over here too, it's same thing, same principle, it's just whichever you like better, triangles or circles. I kind of like triangles for this purpose. And if you're doing mass is equal to rho times volume, there that is. Density is mass per unit volume, that's what we have there. Our volume is equal to mass divided by density. So these will work anytime you have this. Ohm's law, power law, anytime. Distance equal, or speed is equal to rate divided by time, distance divided by time. Anything that you have in a division or multiplication sense, you can use this. If you set them up right, really easy to do. To me, the units are the important thing, because this is in kilograms per cubic meter, kilograms, cubic meter. Kilograms per cubic meter times cubic meter. Cubic meters cancel out, you get kilograms. This is cubic meters. This is kilograms. This is kilograms per cubic meter. The kilograms cancel out, and 1 over cubic meter gives you cubic meter. So units, to me, are the helpful things there, but you can use these things too. All right, that's just a different issue. So symbols and equations. Symbols represent quantities, like rho, mass, volume, or the measured properties. The equations relate them, the mathematical relationships between the properties. Density is equal to mass divided by time, volume, mass per unit volume. So these can describe properties like density. They can define concepts, which is sort of density as well. They can specify relationships, okay? Fuel efficiency, concept, relationship, there's just lots of ways that you can express these. Oh, aren't those beautiful words? More math, all right. This is other kinds of relationships, what we call proportionalities.
There's direct proportionality, and what that means, and then there's also inverse. Let's talk about direct proportionality first.
Okay, you've got two things going on. Actually, there's three, but one of them is held constant. So let's say we're driving from here to Tuscaloosa. Okay? Now, I just picked that because it's in your town. Okay? So any Auburn fans, I'm not being favored. You know, my wife's from Tuscaloosa. Okay, direct proportionality. If I'm driving from here to Tuscaloosa, the time that I drive, as long as I'm driving the same speed, get on the interstate and go. As long as I'm on cruise control, fixed speed. The longer I drive, the further I go, right? The shorter I drive, the less distance I go. That's a direct proportionality. Time and distance are directly related, meaning they increase and decrease the same way as long as the speed is constant, right? Okay. That's a direct proportionality. I'll give you the symbols later. Inversely proportional, that would be like this. I'm driving here to Tuscaloosa, fixed distance, okay, fixed distance. If I drive faster, how much time is it going to take? Shorter time. Larger speed, smaller time. If I drive slower, meaning smaller speed, longer time. That's an inverse proportionality. When one goes up, the other goes down. Direct proportionality, if one goes up, the other goes up. If one goes down, the other goes down. Inverse proportionality, if one goes up, the other goes down. If one goes down, the other goes up. That's an inverse proportionality. Okay? Now, that leads to the proportionality constants. Okay? Now, we're going to come back to that in just a second. But some of these are numerical constants and some of them are dimension constants. I don't know if that's what they mean here, but we're going to get to it. Here is the way we express this. A direct proportionality, if A is proportional to B, this symbol means is proportional to. It sort of looks like the old symbol for a fish. It kind of looks like the Greek symbol alpha. To me, I think of goldfish, okay? It looks like a goldfish. I like goldfish, okay? The ones you eat. Never mind. Okay. This means A is proportional to B. That's a direct proportionality. As B increases, A increases. As A decreases, B decreases. Vice versa. Either way. Okay? Now, to change that proportionality to an equation, here's what we do. Let's see if it's on the next slide. No. Okay. This is your inverse proportional. Okay? As A decreases, B increases. As A increases, B decreases. Okay? That is inversely related. Okay? Now that sort of makes sense, doesn't it? Give me a number, B. What's any number? 6? Okay. Then this would be 1/6. Okay? Give me another number. 9. Is 9's a bigger number, right? Is 1/9 bigger or less than 1/6? That's less. So this would be 1/6 the first time. When you increase this one, you decrease that one, and it becomes smaller. Okay, so that would be 1/9. I think in terms of food, so I think the parts of the pizza. So okay. So how you go from a proportionality to an equation is this. Anytime you see the proportion symbol, like here, replace it with A equal K. Equal K means proportional. B. What that means is this is your proportionality constant. Okay, let's get back to the longer you drive, the further you go. A is proportional to B. Okay, so if this is the time that you've driven, and this is how far you've driven, they're proportional to each other, directly proportional. What's the constant here? Speed. Absolutely right. That's your proportionality. Because remember I said at fixed speed and at constant. Okay?
So there is your proportionality constant. In that case, it was the speed. Okay? Let's go to this one. And then in place of A, you say, in place of the proportionality symbol, you put equal K over B. Okay? Now that was the one that we used, and we said the faster you drove, the shorter the time. Okay? The faster you drove, the shorter the time. Okay? So if B is your speed, and this is your distance, what is it? This is your time. Yeah, that's your speed, that's your time. This is your, remember I said fixed distance. So yeah, exactly right. That's your proportionality constant. So whichever proportion it is, inverse of it, replace the proportional symbol with equal K. Equal K times if it's a direct proportional, equal K over if it's an inverse relationship. Okay. Now, some of these proportionality constants will be strictly numbers. Others, like we had, were dimension. Speed was a dimension quantity. Distance is a dimension quantity. There are others that are just going to be numerical constants. Okay, let me erase my mess so we can see this better. So rather than just being proportional to, when you replace the proportional symbol with equal K, you get an equation. Now the two sides are equal with that proportionality constant, whether it's dimensioned or a pure number, numerical constant. Okay, I haven't been keeping up with our text. Sorry about that. I got carried away with the slides. Remember when we were describing things? We did the desk, they did a chair. Here is a chunk of rock, like we would have in Physical Science 1. How would you describe that to someone else who couldn't see it? Okay? Like you were telling them over a phone. That would be tough. You could do the chair pretty good justice because everybody's seen a chair, but this piece of rock, that would be a lot harder. There's various colors in there, various crystal sizes and other things. So yeah, things would be a little bit tougher there. Here are some of the measurement things. I mentioned several of them. A cubit is from your fingertip to your elbow. A yard is from your nose to your fingertip. An inch is your top joint of your thumb. A fathom is the span from fingertip to fingertip. Now this is for a guy, normal guy. A fathom is 6 feet. I don't know if you realize this, but for most people, fingertip to fingertip is exactly your height. Very, very close. Okay? And most people, fingertip to fingertip is your height. So a 6-foot guy would be 1 fathom. Okay? And of course, the one I mentioned was a foot is a foot is a foot. Okay? For most standard guys. Mine's a little too long. Okay? Different ways of measuring lengths. They have several things here. 50 leagues. Remember Jules Verne? Okay, that was 20,000 leagues under the sea. 130 nautical miles, which are a little bit longer than statute miles, which are 150 miles. This would almost be Atlanta to Birmingham, wouldn't it? 158 Roman miles. I didn't know there was that big a difference. It's not much different, but just a little bit. That would be 1,200 furlongs. That's what they measure horse racing in. 12,000 chains. That's what you measure land with. And you also measure, because 4 rods make a chain, that would be 48,000 rods. 452,000 and some odd cubits. Okay, cubits, okay, are 792,000 feet. So that's just a few of those. And then this were the things you saw on my slides. Oh. They left off, back when we were talking about the prefixes, this table in your text on page 6, when you get your
your basic unit for your SI units. That could be meters, it could be grams, it could be liters, it could be amperes, it could be anything. What your basic unit was, seconds, but we usually don't measure seconds this way. 10 more than that is, going up is deca, D-E-K-A, like decade, hecto, like hectare, kilo, 1,000, and on the street, that's what a kilo, no, we don't do that, okay? A kilo is 1,000 grams, okay, a kilogram. Mega, now they start being capital M because we already use little m down here for milli. We use a little Greek m, micro, for micro. That's a mu is the name of that. So we use a capital M up here for mega. So since we use capital M for mega, all the rest of these are capitalized. Giga would be a billion. Tera would be a trillion. Peta or peta would be 10 to the 15, that's for quadrillion, and exa, which is 10 to the 18th, is a quintillion. Sounds like a dance or something, okay? Going down, a deci is 1/10, a centi is 100, a milli is 1,000. Those go down by 1 powers of 10. Then you go to 3 powers. 1 millionth is a micro, 1 billionth is a nano, 10 to the minus 9 nano, okay? Y'all don't remember that. Pico, 10 to the minus 12, that's 1 trillionth. Femto is 10 to the minus 15, femto 15, 1 quadrillionth, and then atto is 1 quintillionth, 10 to the minus 18. I'm getting tired of holding that. Okay. Now, here's one more that is pretty useful in metric. Okay? If every one of these little blocks here was a cubic centimeter, okay? Cubic centimeter. Centimeter, remember the distance across your little fingernail. That's a centimeter. So this is a cubic centimeter. Really small cube of sugar. Really small. Well, if you had 10 of those centimeters, that gives you a decimeter. 10 centimeters make a decimeter. So 1 square decimeter would be 1,000 cubic centimeter. 1 cubic decimeter would be 1,000 cubic centimeters because it's 10 times 10 times 10. Or a cubic centimeter is, another name for that, is a milliliter. Okay? And by the way, every cubic centimeter is 1 gram of water. So that would be 1,000 grams or 1 kilogram of water. Well, we also call that 1 liter. So a liter of water is 1 kilogram of water. So if you ever buy a liter Coke, which I don't know if they sell them, they do 2 liters and 3 liters. I don't know if they do 1 liter. Thomas, what's your container there? What's the capacity of that? Do you know?
1,000 milliliters.
Okay, that's 1 liter. That is a liter. How would that compare if you poured that into a quart container? Not what you got there, but if that was full, you'd spill. Because a liter is a little bit more than a quart. Just to give you an idea. They're very close, okay? But the thing to remember, a cubic centimeter is the same as a liter. So 1,000 cubic centimeters, is a milliliter. 1,000 cubic centimeters would be 1 liter. And that, by the way, is 1,000 grams, which is 1 kilogram of water. Okay. So when you fill that up, that would be 1 kilogram of water. Okay. Now, why did I say all that? Just to give you an idea, for one thing. Let me give you a couple of examples of that. I had one and now it's flying the coop. Oh yeah, this is the automotive trivia. How do y'all measure engines? Say again? Cubic inches, quite often. Or nowadays they do. Yeah, now they do liters, which is thousands of milliliters. So what's
say, a fairly small size engine?
I think we got a 1.5 now, which is 80 cubic inch motor.
Yeah, okay, it's pretty small.
It's really small.
Okay, really small. Back in the day, though, they had some a lot smaller than that. Okay? In fact, one car company, not U.S., one car company, pretty major car company now, started off as a pretty major motorcycle company at the very beginning. Anyone remember what that was? Honda. Okay. Now, I think their first car that they built was, I'm not sure, but it basically had a motorcycle engine in it. And it was a pretty small car, but that was a pretty small engine. And they called it, let me see if I can remember. They used, for some reason, they're a Japanese company, they used Roman numerals, which was bizarre, okay? And it was a 105 cubic centimeter, and back then they used cc's. 105 cc, which is 100, yeah. So that was a pretty small engine, right? You know what they named the car? A what? Civic. They just put another I in here and forgot a C. That's what I heard is how they came up with the name Civic. 104 cc's, which is really small. Okay. So that's, really small. Okay. Now, everywhere else in the world pretty much uses metric, not U.S. customary. And this is why I was asking the thing about ports and liters, okay? When I was in the Navy, the first midshipman cruise that I went on, this was between my freshman and sophomore year of college, I went to Little Creek, Virginia, okay, and got on board one of the three oldest, I had orders for one of the three oldest LSDs, which is Landing Ship Dock, it's an amphibious ship, that I was supposed to go to, one of the three oldest ones left from World War II in the U.S. Navy. It broke down before I could get there, so they changed my orders to another one, which is the second of the three oldest LSDs left in the Navy. And by the way, my dad got such a kick out of telling everybody that summer, especially at church and places, they said, well, where's Charles this summer? Oh, he's on an LSD trip. But that was, his sense of humor. Hopefully y'all know what LSD, never mind. But it meant landing ship's dock. Okay, but, so I was on that. We went across the Atlantic, got to Rota, Spain, and we were in a group of 5 ships, and we got into Rota, Spain, and there we replaced 5 other ships that had been on a 6-month deployment in the Mediterranean. I didn't get to go into the Mediterranean, just barely close to it, and then got on those, and the 3rd ship I was on was the 3rd of the 3 oldest LSDs left in the Navy. And by a year after I was there, the one that had broken down, they scrapped. The other 2 they sold to Argentina or somewhere, so we didn't own them anymore. So I was one of the last people on, well, not the last, the ship's company was there. But anyway, I was on an LSD ship. But anyway, when I got to Spain, this was about the time that the gas prices were going up really rapidly. Y'all may not believe this, but when I was in high school, first driving, they would sometimes have price wars in a town between the service stations. And there were sometimes, I remember, buying gasoline for 19.9 cents per gallon. For $1, you got more than 5 gallons of gas. Not much more, $1. Well, by this time, the prices were going up pretty rapidly, very rapidly. And I remember what it was, and I don't remember now what the numbers were. Nothing like it is now, but still we thought it was really expensive. And got over to Rota, Spain, and since we were leaving this ship, they took us to the base, and we were riding in the bus, going to the base, and I saw the service station up there. I said, oh, it's because it's the U.S. Navy service station. We're paying prices like they did in the back at home. Because the gas prices were a little bit more, but not a lot more. Until we got closer to the station and realized that was price per liter. So they were more than 4 times. We thought it was bad here, but everywhere else it was more than 4 times. Well, more than 4 times what we were paying in the States. So no, they were paying Spanish prices, not U.S. prices. So just to get an idea, quarts are very similar to liters. So liters are a little bit bigger than a quart. Okay. Have I finished all this? I think the rest of them pretty much were in on the slides. Okay. I did forget this, and this is important because this class is, let's go back a little to where we were talking about then. I should be keeping up with the book. I just got to talking too much. Okay, density ratio. Let's do it here. All right. Example 1.2 is on your page 9 for those who have a book. So don't ever let me pass these examples. We did in Physical Science 1. We don't in Physical Science 2. 2 blocks are on a table. Now, I don't draw tables very well, but let me give it a shot anyway. So let's say this is a table, okay, pretty ugly table, okay, but that's a table. You got 2 blocks on the table. There's a block, and there's a block. And these are supposed to be 3-dimensional blocks too, so I do that even worse, okay. Okay, something like that, 2 blocks on the table. Block A has a volume of 30 cubic centimeters. Let's call this block A, and its volume for A is 30.0 cubic centimeters. Okay, now time out for just a moment here. Why in the world did they put that 0.0 there? If they were meaning 30, why didn't they just say 30? What does the 0.0 mean? Second?
It's something behind a 0.
Okay. Okay, yeah, that's a little bit of it, but the main thing is this. That's precise to the nearest tenth of a cubic centimeter. If you say 30 cubic centimeters, that could be just precise to the nearest centimeter. This is precise to the nearest tenth of a centimeter. It's more than 29.9 and less than 30.1. In fact, it's more than 29.95 and less than 30.05. That would be that precise. Okay? So it's significant digits is what we call it. I thought that's what you were saying. Okay? Now, and a mass, so the mass of block A is 81.0 grams. And again, that's to the nearest tenth of a gram. That's what the 0.0 means. Block B, on the other hand, this is B. Okay, I can see the B in that. Has a volume. So the volume of B is 50.0 cubic centimeters. And the mass of B is equal to 135 grams. Okay. Which block has the greater density? Anyone want to hazard a guess? 81 gram block or the 135 gram block? You say it's probably denser, okay? How do we calculate density? Okay, we say rho of A is what? Mass of A divided by volume of A. So that would be 30.0, no, get my numbers right here. 81 grams divided by 30.0 cubic centimeters. Okay, I can almost do that one in my head. 3 will go into 81. Is that 27 times? Yeah. No? Yeah, I think so. So that would be 2.7 grams, 2.70 grams per cubic centimeter. Did I do it right? Okay, 2.70. Now, why did I put a 0 there?
Significant digit.
Because if you have 3 significant digits there, divided by 3 significant digits there, you need 3 significant digits in your answer. I got 2.7, but because there's no more digits there, I have to put a 0 to get my 3 significant digits there. Okay? So that's the density of block A. What is the density of block B? Mass of B was 135 grams, and the volume, I thought I would say velocity, volume of B, I've already written volume of B, duh. It's getting late, folks, as if you didn't know that. That was 50.0 cubic centimeters. Are those the same precision here? 3 significant digits, 3 significant digits, yes. And what if we divide that? What do we get? It's also 2.70 grams per cubic centimeters. So the odds are these are the same materials. They're the same density, it's probably the same materials. And in fact, if you look at the table that is the top of page 9 when you get your book, this table has some of the common densities of some common substances. Aluminum is 2.70. These are probably both aluminum blocks, okay? Not aluminum block engines, but aluminum blocks, okay? 2.7 grams per cubic centimeter. 2.70 grams per cubic centimeter. Copper, much denser, almost more than 3 times as dense. 8.96 grams per cubic centimeter. Iron is not as dense as copper, but almost 7.87 grams per cubic centimeter. Lead, way denser, 11.4 grams per cubic centimeter. Water, of course, is 1.00, as many as you want to put, grams per cubic centimeter. Seawater is a little denser than fresh water, 1.03 grams per cubic centimeter. What's the ramification of that? Seawater, second?
Salt.
Yeah, because salt's in it, and that makes it a little denser. But what's the result of that? Take back Archimedes again. Have you ever swum in the ocean or the Gulf?
OMC's higher.
Yes, you float higher because water is denser. Okay, you displace that volume of that mass of water or weight of water. Mercury, whoa, 13.6 grams per cubic centimeters. Now, what's unusual about mercury?
You can, if they a liquid form.
It's a liquid.
Yeah, you touch it and it'll go into your skin.
The what?
You touch it and your skin will soak it up into itself.
Yeah, and it's also a carcinogen. You don't want to be touching it because it can cause cancer. Okay, but it's a liquid, even though it's that dense. And the ramification of that, if you drop the lead ball into a pool of mercury, the lead is going to float because mercury is more dense than lead. Gasoline, a little less dense than water, 0.68. The ramification of that is when you have an oil spill or a gas spill, it's going to float on the water, not sink. which is not good for animal life in the water because they get the oxygen from the air, and if you have a film on top, they're going to be choked, and they will die. Okay,
That's why oil spills are very bad for the environment. Very bad. There's also in this text little things like concepts applied, density matters, and they talk about sharks and cola cans. I don't really see why they compare those. But one thing about a shark, it's denser than water. And one of the problems with that is sharks can never sleep. If they slept, they would sink to the bottom. So they're always having to swim. Never can be still. If they're still, they sink. I'll let you read that. Okay. Anyway, we did example 1.1. Let's do 1.2. Okay. A rock with a volume of 4.50. So the volume of the rock is 4.50 cubic centimeters. Good unit for that. And has a mass. So the mass of the rock is 15.0 grams. What is the density of the rock? What would that be? What's the symbol for density? Rho is equal to mass of the rock. This is the density of the rock, mass of the rock per volume of the rock. And that would be 15.0 grams divided by 4.50 cubic centimeters, if I could write. And what does that give us? Punch that on your calculator. Something greater than 3 1/3. 3, is that what you said? 0.33. How many 3s should I put? Stop there. Okay. Grams per cubic centimeter. Your calculator is going to put as many 3s as it's got places. You round to 3 significant digits. So we stop at 3. 3.33. Because the next digit was also a 3, you throw it away. You don't back round it up. Okay. Normal rounding. And that's what they got to. Good for them. Okay. They talk about another concept applied, a dense textbook. Well, you can calculate the density of the textbook, put it on a scale, especially one that measured mass, kilogram. Okay. This is going to be pretty close to a kilogram, I think. Your little ones will be less. Okay. Put it on a scale, and then you can estimate the volume by length times width times thickness. Multiply those together. If you're doing kilograms, then you really should do meters. So probably better to do how many grams it is, and then do these in centimeters and get grams per cubic centimeter. Now, myths, mistakes, and misunderstanding. That's another thing this book likes to have. And you can read that. It, to me, is a rather lame one, just talking about gas in a can, a Coke can or something like that. Now, there's also another concept applied here. Sorry to keep going over these things. This is talking about the inverse square relationship. Lots and lots of things operate by what they call an inverse square law. Okay? And here's what they're talking about. If you have a point source, say of light, of sound, of just about anything, and it's radiating outward at a uniform rate, when you get one distance away, that identifies a square of one size, right? If you go twice the distance, and then you get this the square in here, you can break that into exactly 4 of these little squares. So as you double the distance, your area is increasing by the square of the distance. So that's 4 times. You go up to 3 times the distance, now you have 9 squares in there. So again, triple the distance, 3 squared is 9. That's what's called an inverse square law. That works for things like gravity, it works for light intensity, it works for sound, just about anything. You double the distance, you
square that doublet. Square the 2, and you get 4 times. Now, one example I do for that, my wife, unfortunately, likes to read at night. She has this little clip-on on her book or Kindle that provides her light. Well, what if she hung that from the ceiling? Could she still read by it? No, because right here is that distance away. You multiply the distance by 100 times to get it to the ceiling, and now you've decreased the light intensity, not by that many times, but by the square of that many times. So no, that wouldn't be good to suspend from the ceiling. Okay. Now, I was sort of missing some of this stuff because they didn't have any slides on it and I wasn't paying attention. Okay, before we get to that, let's back up to this. Okay? Now, I'm not going to write all this down, but I'll go over it. Remember, one of the topics here was making problem solving easy or something like that. There in the book, they say how to solve problems. Okay? And you may have noticed when I was solving these, I was kind of using this. Number 1, step 1, read through the problem and make a list of the variables with their symbols. Notice I put M sub A, M sub B, V sub A, V sub B, rho sub A, rho sub B. Make the symbols so you know what you're talking about, okay? They say on the left side of the page, the right side, I don't care about that. Get them down there somewhere that you can understand them, okay? Including the unknowns. Now, I didn't put that down with a question mark, but what we're looking for was density. That was the unknown. I wrote down the ones we knew, and then wrote also the one we were looking for. So that's the step 1. Now, I don't go by these steps completely, but you always do some form of it. It says, inspect the list of variables and the unknowns. Identify the equation that relates them. Now, I think I asked you, what relates mass and volume? And you said density. Density is mass per unit volume. So identify those equations. Write the equation. They say on the right side of the paper. I don't care what side of the paper you do. Okay. Now, to me, they left out one. And I did it, even though it really didn't have any pertinence to the problem. Sometimes drawing pictures are worth thousands of words. Okay? Because if you see sort of the relationship, then maybe the formulas and equations will come to you a little better. Okay? So I like to put that first. When I'm writing down those identifiers, I also draw a picture, if it's helpful. Sometimes it's not. I drew an ugly table and put blocks on them, but they were still ugly. Now, then you solve the complete. Now, here's what they say. You write down the equation or the formula, like rho is equal to mass per unit volume. Okay, what if you're looking for volume? What they suggest, solve that equation for volume, like we did earlier, multiplying or dividing, doing whatever it takes to solve for the one you're looking for. That's how the book suggests. I call that the chug and plug way of doing it. You get it into the thing that you want, and then you plug in the numbers and you just do the math. Okay? A lot of students seem to prefer to plug and chug. They write down the original thing, put the numbers in there, and then have to manipulate to solve for the one they want to. It works both ways. The book always suggests that you chug and plug. Solve for the variable first, and then plug in the numbers. Now, by doing it that way, then you can wait and compare your units later. If you're chugging and plugging, or plugging and chugging, that means you better get the units right before you start the solving. So if you don't solve in the way they say here, be sure you get units right. So when I'm listing those things, if one of those units would have been inconsistent with the others, deal with that first. Always deal with that first. Okay? Now they say to substitute the number values in, do the mathematical operations, but also keep your units and make sure the units balance out correctly too. If you get a volume measured in grams, you've done something wrong, okay? Because grams measures mass, not volume, okay? So be sure you keep your units. They're your friends. They'll help tell you whether you've done some stupid, made some mistakes somewhere. Okay. And another thing, ask yourself if they're reasonable. If we had to come up with a density of 270 grams per cubic centimeters, I'd say, whoa, here, look at our table. We don't have anything in there close to that density. That doesn't, we've done an error somewhere. They say, for example, 250 meters per second is way too fast for a student running. So go back and recalculate. The unit for speed is not liters. So if you come up looking for speed and you come out in liters, no, you've done something very, very wrong there. And then they say, step 8, draw a box around your answer. Yeah, I don't care if you put a box around your answer, but they do it in the book, so you can do that. Okay. This is not an example in the text, but it's what they call an example problem in the text. Okay? And based on one of those numbers we look like. Mercury is a liquid metal with a mass density of 13.6 grams per cubic centimeter. I held that up in the table. I read that and I write it down. What's the symbol for density? Rho is equal to, and they tell you 13.6 grams per cubic centimeter. That's what they told you. So I write it down. The mass density of 13.6. It says, what is the mass? So mass is what we're looking for. We don't know what it is. That's the question. What is the mass of 10.0 cubic centimeters of mercury? What's that a measure of? 10.0 cubic centimeters. What are we measuring there? Cubic volume, exactly. Okay, that's not volume as in loudness, that's volume as in 3 dimensions. Okay, so what formula or equation relates these 3 units together? Say again? Say again? The formula or equation, huh? Okay, you're doing. The one we had was rho is equal to mass divided by volume. That's how we defined it, right? But we want to know mass, so that's what Patrick was doing. He was solving for mass, okay? So let's multiply both sides by volume to get rid of volume in our denominator. I don't like it down there. So that gives us mass is equal to, I'm going to put rho times V, okay? Well, rho is 13.6 grams per cubic centimeter. Multiply that by 10.0 cubic centimeters. That's your volume. Notice here your units go out, your cubic centimeters go out, and that's an easy thing to multiply. Multiply by 10, you move your decimal one place, 136 grams. Is that a good unit for mass? It's a great unit. That is what we measure mass in, grams. So, sure enough, that's what we got. It took a little bit longer to do, but they got the same place. Okay. Finally now, we're ready to go to the nature of science. I realized we went all that time and I hadn't kept up with the book. Oh wait, there was one more. I thought this was going to be on the slide, but it wasn't. I just happened to notice it. I'm going to do my best to draw a circle. Now, that's probably not a very good circle, Let's live with it. If that was a circle, what do we call that dimension there? That's the diameter of the circle. Okay? Now, if that circle did complete itself there, let's just imagine it did. Okay? Does anyone know the formula or equation for the distance around the circle? Let's say we started here and went all the way around that circle and came back to there. What do we call that distance? Circumference. That's the circumference of the circle, the distance around the circle. It's like the perimeter of a square or rectangle is the circumference of a circle. Does anyone know a relationship between the circumference and the diameter of a circle?
The circumference is 2 pi r.
Okay, 2 pi r. Okay, that is pi times the diameter. Okay? Circumference is equal to pi times the diameter, or as Patrick first says, circumference is equal to 2 pi r. What's r? It's the radius of a circle, which is exactly half a diameter. Okay? So 2 radii make 1 diameter, because a radius is half a diameter. Okay? So those are 2 formulas there, which you can now say that the ratio of circumference to diameter is equal to what? Say again? Take this formula here, divide, that's equal to pi. And what is pi? It's a number, 3.141, blah, blah, blah. It's an irrational number. It goes on forever, never repeats itself. And it's rather bizarre, because being an irrational number, that means it's not a ratio of 2 integers. So what that's saying, if you had a circumference with exactly an integral value, your diameter couldn't be an integral value, because that would be the ratio of 2, and it's not. So don't ever think if you can measure a diameter exactly, you can't measure the circumference exactly. Or if you can measure the circumference exactly, you can't measure diameter exactly, because pi is an irrational number. So it's rather strange. But that is a numerical constant. It's a ratio that's a numerical constant, because there are no units associated, because your circumference is the same dimension as your diameter. They could be in centimeters, they could be in miles, they could be in kilometers, they could be in furlongs. Whatever they are, they would need to be the same. But the ratio would always be the number pi. Okay, now I think we're through with that. Let's move on to 1.7, which is the nature of science. Been trying to get there, but haven't made it yet. Oh, there it is. Okay, let's get the Honda out of the way here. Okay. Now, this is a rather bold statement. They're saying science actually only began about 300 years ago. What? We didn't have science before then? In many respects, not, because science is kind of the organized study of our environment, stuff like this. Sure, we have people that they didn't even call themselves scientists. They called themselves natural philosophers. And they came up with formulas and equations. Archimedes was one, okay? He was as close to a scientist as you could get back then, but he probably wasn't exactly a scientist. He was quite an engineer in some senses. I'll tell you why I say that. Remember I said his king was pretty powerful, but he had a very small kingdom. The main reason he was powerful, he had Archimedes on his side, okay? When some big, powerful naval kingdom tried to attack him, came in, back then it was all wooden ships, of course. Archimedes set up an enormous lens up on the mountain outside the harbor, and it happened to be in the way that the sun shone, and that lens, it was a convex lens, and it focused the sun rays on the ships, and it burned them up. He knew enough science to do that way before it was called science. He also, I think, was the first to come up with a catapult that he could throw rocks or burning pots of tar at those ships. That didn't do good on the ships either, okay? So he came up with all kinds of things that fought off much bigger armies and navies and other things. He was an incredible, but he wasn't counted a scientist, which I think is unfair. He was a pretty good one. But the reason they say this is that it was probably after Archimedes a good time that the ancient Greeks, not as ancient as Archimedes, but others, they had three really big named natural philosophers. The first of them was Socrates, who actually was more of just a pure philosopher. He had so many radical ideas, they didn't like him anymore, so they made him drink poison or recant what he was doing. He drank poison. That was his famous thing. One of his students, I can't remember the order of these, I think was Aristotle. Okay? And Aristotle was more of a natural philosopher. He observed nature and came up with ideas. And they were good seeming ideas. The trouble is a lot of them were wrong because they were just ideas. Okay? And then the third one went back to almost being more of an other philosopher, and that was Plato. He was pretty good in his own right too. But about 300 years ago, this was several centuries after Aristotle came up with this thing, and no one argued with Aristotle, by the way. If Aristotle said it, it got to be true. You know, he was that bright. Okay? Well, about 300 years ago, this one Italian named Galileo, he took some of the ancient natural philosophers, think Aristotle now, who only thought through the problems and called it science. Well, I don't know if they called it science, but that's what it was treated as if that was truth. And he tested some of the things. That was the difference. He tested their theories, their thoughts, their ideas. And he found out a lot of them were absolutely wrong. Okay? Now, the interesting thing here, Galileo lived down in Italy, a town called Pisa, Italy, not P-I-Z-Z-A, but P-I-S-A, the place famous for the Leaning Tower. Okay? That was where he was from. And it was, I think, the very year he died, up in England, was born this young kid named Isaac Newton. Now, Isaac Newton almost wasn't born. Okay? He was born so prematurely. Most babies at that time were that preemie, didn't make it. Somehow he made it. Okay? Sadly, his father had died a couple months before he was born. Okay? So he grew up without a dad. His mother remarried, and he didn't want to raise somebody else's kid, so he sent Newton to live with a grandmother, and he started his own family with Newton's mother. After a few years, he died, and she brought Newton back and said, "Why don't you farm for me? Because we got to support the family." He was a terrible farmer. He was a thinker. But he read much of Galileo's work and many others, and that's why these two are taken together. Sort of like the year he died, Newton came along, looked like they tag team on the way up and down. I don't know, I just made that up. But this was when most people today consider that science began. Why? Here's the additional component that Galileo and Newton did that the ancient natural philosophers didn't do. They based their understanding upon experimental evidence. They didn't just think through the problems, they tested it. Did experiments, see if it came out the way they thought it would. And if it did, fine. If it didn't, try something else. That's the big difference here. So with them was born what we call the scientific method, and that's why they say science was born here. Okay?
Now, the ancient philosophers observed some aspect of nature. They did a great job of observing. Okay, fantastic job of observing. And they proposed great explanations for something observed. Okay? The natural philosophers did that. But what they didn't do, and what Galileo and later Newton did, and most of the scientists since they proposed the explanation, they would use that explanation to say, okay, if this is true, then if we did this, this should happen. That's making predictions. Aristotle and those guys never did it. They just thought through, looked at it, and said, this looks like this is true. Write it down. Okay. Not Galileo and Newton. They would then say, okay, if that is true, then if we do this, this should happen. Make predictions. Test those predictions with experiments, okay, or more observations. So they would do that. And if it came out good, they said, okay, that seems to work. Then what if we did this? And what if we did this? Okay? But if they didn't work, they say, whoa, okay, something must be wrong there. Either our explanation is off or our prediction was off. One or the other. Well, then you modify the explanation and then go back and test again. Make more predictions. Test those. And if they start coming out right, they say, hey, I think we got it now. Okay? That's when the scientific method was born. Only about 300 years ago. Even though we had some really good scientists, so to speak, before then, they didn't necessarily do this. I bet you, I'm a big fan of Archimedes. I think he was doing some of this back then, but he didn't formalize it. Just based on things I read. Like that crown thing, He said, hey, if this is true, then this should be true. He tested it. He found out. Okay. Never knew I never heard the rest of the story, whether the crown was pure gold or not. He found out, though. So here's sort of a kind of a wacko example, way beyond what we've been talking about, of the scientific method. What are atoms made of? Well, number one, that's not a very good sentence, is it? Dangling preposition at the end. Okay? Well, we know today, they didn't know way back then, that there were negative electrons that orbit a positive nucleus. This is what we're going to be talking about in a couple chapters hence, certainly in chapter 8. Got a positive nucleus and then negative electron going around us. Now, when you collide two atoms at great speeds, you'll sometimes produce free electrons and nuclei by themselves. Okay? They won't stay that way for long, but they will be that way for a bit. Now, if you collide two atoms yielding electrons and collide them even harder, you'll sometimes break up and find protons and neutrons. Well, the electrons were already there. Where did these come from? They must have come from the nuclei. So then they discovered the nuclei, the core of the atom, is made up of protons and neutrons. Okay? So now we know the atoms are made of electrons orbiting nuclei, but the nuclei are made up of protons and neutrons. Well, guess what? Let's collide with even more energy. Hit them faster, hit them harder, see what comes out of it. And this is really the basis of what we call particle physics. They have discovered all kinds of particles that live inside. Neutrinos, positrons, muons, pions, bosons, okay. A whole string of things like that. Okay. To me, that's a fairly lame example, but it is it's pretty good. Let's just keep hitting them harder and see what happens. Now, some general scientific activities. Okay? This is basically putting together what we were just saying. Collecting observations, observing nature, seeing what we see, developing explanations. Okay? We called that before
or what did they say it before? Yeah, explanations, okay. Developing explanations. Here's where the science comes in. Test those explanations. Make sure they do what you think they're doing. If they don't, develop new explanations, okay? If they give you things you weren't expecting, then test some more and see what else is out there, okay? So, here are some of the terminologies. They talk about them here. We hardly ever will use them later in the text, so that's why some of this gets to me to be a little useless, maybe, but not quite. Hypothesis. That's one of those tentative explanations for some observation. We've observed nature. We think we see a thing. We say, we think this is why it's happening. That's our hypothesis, okay? Then we design and perform an experiment, which is the recreation, that's not recreation, but recreation of an event or occurrence to test the hypothesis. Now, let me give you an example. When I was at the University of Georgia, I was an agronomy major, soil science, and I worked under a guy who was soil fertility, and I was doing some mineralogy. But he was suspecting that corn growth in some of the soils in Georgia was really pathetic sometimes, and he was thinking liming had to do with the problem. The soil was too acidic. Second?
Too much calcium.
Not too much, not enough. Okay, lime adds to calcium. Okay, this is too much acidity. Okay, so his hypothesis was these low yields are because too much acidity in the soil. So his experiment was to take this pot of soil, okay, and let's lime it at different levels, okay? Now, so that was going to be this experiment. Recreate an event or occurrence to test the hypothesis. So we're going to put, and basically they take a big plot of land and do it into squares or grids of some nature and make sure that everything in those grids are as close to the same as possible. Same soil type, same water, same everything. The only difference is how much lime we're going to put on each one, okay? So that leads to what we call a controlled experiment, comparing two situations with all the other factors alike except for one. So what he did, now, here's the other issue. What if that was just poor soil? And the issue was that it didn't have enough calcium, or it didn't have enough nitrogen, or it didn't have enough potassium, or phosphorus, or something else like that, okay? So what he would do, what we did, was we fertilized every plot exactly the same. Exactly the same. Well, we, number one, did soil tests on all the plots and make sure they were very close to the same levels. Then we fertilized them exactly the same with everything except the lime. So we kept all the factors alike except one, the lime. So your control group was the fixed set for comparison. Let's say the one with absolutely no lime on it. Okay? Everything else the same, but no lime. The experimental group differs from the control group by that one influencing factor. Now here's what else he did, not just to do lime or no lime, he did different levels of lime. So the control was no lime, then he put, I'm just going to make up numbers, 1 pound per acre, 2 pounds per acre. Yeah, it's not going to be that. It's going to be much bigger than that. 1 pound per square, 2 pounds per acre. He figured it up in per acre. So that was his experimental group, and then he saw what would come of that. And sure enough, with all the fertility the same, the lime level didn't make a difference. But what he also found, it would make a difference at a certain point and then either flatten out or actually decrease. So too much lime was not good either, but there was some optimum amount. And that's why he did several levels at once. So that would be that. Now, that was basically an active kind of experiment. There are others that are you do after the fact. My wife is a researcher at UAB, and she studies a certain virus called cytomegalovirus. It affects children, infants, well, fetuses in the womb. You could catch CMV and you wouldn't notice it. You might feel like you had a little bit of a cold, a very mild case of flu or something. Be over it, done with. No negative effects at all. You just feel a little bad a day or two, and that's it. A woman who's pregnant is affected with CMV. She may feel that, but the baby could be far worse. Okay, because the virus seems to really attack the fetal tissue really badly. Now, most of the time, absolutely no problem. But a certain amount of time, there's hearing loss, there's macro or microencephaly, big brain, small brain, just a whole bunch of stuff, and sometimes death even. So she's been studying this disease. I remember when she was doing her doctoral dissertation, she was looking at births at University Hospital, and over years, and they were testing all the babies by that time for CMV. So she would find those that were CMV positive, and then she would go as her control group. She had all the births there, the records there, stacks of paper, and go through and find a child who was born on as close to the same day, with the same sex, same socioeconomic group, same race, same gender, okay, same everything. She tried to control as much as she could, except the fact that one child was CMV positive and the other was CMV negative. So she had to do it in the reverse. She couldn't set up and infect people. You don't do that with people. You can do that with plots of land. So she said it that way. Her control group were the ones that were CMV negative, and the experimental group were those that were positive. Then she would try to contact those mothers of both groups, and find out as much as she could about what had happened. She found out that multiple sexual partners was a likely cause of some of that. I can't remember all the ones that did, but she was able to pinpoint certain things that might have caused it and possibly contributed to the fact they did. And based on that, she's done since then, and they found out that most of the unknown hearing loss among young children probably is attributable to CMV. There's some you can't tell where it came from, but most of it could, and that's some of the research she's done. But it's because she looked at control groups versus experimental groups. Okay. How are we doing? Not much longer. This book is kind of big on pseudoscience. What do we mean? What does this prefix pseudo mean? Anyone have an idea? What is a pseudonym? Say again? Not quite, yeah, you're really close to it. When I say what's a pseudonym, nym is the same root as noun or name. So a pseudonym would be somebody like, an author who writes under a different name. I was trying to think of some of the women that have done that. A.A. Milne wasn't A.A. Milne. He wrote Winnie the Pooh. He was a pastor, and he thought he'd be ridiculed if he wrote his own name down there. So he wrote under a pseudonym. So this is a false, sort of like opposite science, false science. This is misleading and often absurd claims of scientific results. That's what I was saying about the internet. A whole lot of stuff out there is nothing but garbage. It's misleading, sometimes really absurd stuff saying that it's true. Actually, in my Physical Science 111 class many years ago, a student brought in something really excited about that this meteorite had fallen somewhere in South America and was making people sick. okay? And it was big in the news that way. And it was all over the internet that way and stuff. And then when they sent the epidemiologists down there, the people who studied diseases, they found out they had common colds, but because the meteorite fell and someone got sick, they were assuming that, so everybody started thinking whatever they had was being caused by that, and they found that it wasn't. Misleading, that was pseudoscience, okay? When they got the actual professionals down there, they found no basis for it. Here are some of the tests for pseudoscience. What is the academic and scientific background of the claimant? If it's Joe Blow politician, there's a good chance it's not science, okay? You know, if there's no academic or scientific background of whoever's claiming it, the odds are it's pseudoscience. What is the history of review by scientific peers? This is almost saying the same thing. Has this work been looked at by other people? Okay, I mentioned my wife was a researcher at UAB. It is really hard to get funding these days because the federal government isn't providing funding to National Science Foundation, National National Health Foundation, American Health Foundation. Yeah, all these things, you know, they're just not getting the funding they used to. So it's really hard. So every grant that you write, it gets reviewed by probably a handful of other professional scientific peers, and they can get some really good scores, but they don't have enough money to fund them. So she's been writing grants for years now and just getting a little bit funded there, a little bit there. It's really a terrible time to be in science right now. Okay? History of review by scientific peers. If they don't think it's any good, it's not going to get funded. Or even after they've written the paper, when people submit a paper to a journal, the journal will usually send it out to at least 3 reviewers, and sometimes they'll actually ask the reviewer, do everything this guy said he did, and see if you get the same results. That's what we mean by that. Participation in scientific institutions and organizations, this would be things like those journals, those things. One of my professors at Georgia Tech was the chief editor of some big international mineralogy journal, okay? Crystallography, I'm sorry, that was crystallography. And he's the one I talked about that when he got to go to Rio de Janeiro, he went in to flush the toilet just to see the water flow in opposite directions. Damn, okay. But anyway, is the claim published in peer-reviewed journal, that's what I was talking about, and independently validated by others. That's where they actually send them out and have someone else do identically what you say you did in the experiment and see if you get the same result. Now, unfortunately, I don't know if you've heard phrases like this, but at a lot of the major research institutions, there's this little phrase they say, publish or perish. In other words, if you're not producing new material, getting published, getting a claim, you get canned. Okay? And it happens. And sometimes that is so much pressure on people because you can spend years working on a project and find out something just isn't going right. You know, you're not getting what you expected. You're going through those hypotheses and every one of them is coming up negative. Well, you can't publish any of that, so therefore you spent all this time. And sometimes, and they've had some pretty major, well-known institutions, they've had a few scientists who've actually falsified things and said they got results they didn't get. How they discovered, they had sent that to others and had them reproduce it and say, no, we can't get these results. Went back to the guy, and the guy finally said, no, I didn't have enough evidence to show if I didn't come up with something, I was going to get canned. So I thought this was likely. It didn't happen. That's pseudoscience. Okay. Oops. It's almost time. We're going to have to start next time with laws and principles. We don't have much left to do in this chapter.
let me mention this one thing. They have a blurb at the top of page 15, Science and Society. These are usually really good blurbs to read. This one is basic versus applied science. Pretty good one to read. I would definitely pay attention to that. And we're going to start on page 17 next time, and that's laws and principles.
We'll do a lab next time?
Yeah, we will do the lab next time, because we only have a few pages to go in chapter 1. We'll finish chapter 1 probably within the first 15, 20, 30 minutes, something like that. Then we'll go on and get started in chapter 2, and then we'll go, here's how it'll pan out. We'll continue in chapter 2. Chapter 2 is a long chapter. We'll go pretty well in that. Then at 5:45, we'll stop and have the lab for chapter 1, okay? And that means the next Tuesday, we will continue in chapter 2. I'd probably get far enough along to have a lab for chapter 2, but only do 2 hours in chapter 2, 2 hours of lab for the first lab in chapter 2, then 30 minutes for the test in chapter 1. So that's kind of how things will go. Okay, good deal. Y'all were very good to endure all that. That was a long time sitting. Way to go. Good deal. Paper topics already.